Let's talk about Monte Carlo simulation. Sorry. Monte Carlo methods. I'd like to talk about two main methods. Number one, estimating area and volume of, or I can say arbitrary objects. The formula is simple. All you have to do is, if you have an object, this object will have area AO, that's area of the object, and I want to find this area. So what I will do, I'll put this object inside another object whose area is already clear. I know the area. For example, this is length, this is width. So I put this object in here. Let me make it blue. And the formula says, because this guy will have area, let's say square. If you want, you can make it a circle. In this case, you're looking at the radius. You can put it inside a rectangle. You can put it inside any shape. You can put it inside an oval shape, for example, any shape. Just for simplicity, we use a rectangle, length and width. So the area is length times width. And the Monte Carlo formula is, you are going to throw points randomly into this area. Then you are going to estimate how many points fall within this region and how many points fall outside the region. And the formula goes this way. Those within this region, you can call them N in, and those the total number we throw, we can call it N total or NT. So the area is this, the formula is this. So area of the object divided by the number of points that fall within the object is equals to the area of the square divided by the total number of points. So n is just the number of points. So number of points. And therefore, from this you can say that the area of the object is number of points inside divided by the total number times the area of the square, which is length times width. Now, where is the Monte Carlo come in? It comes because this guy we already say is length times width, or you already know it. You are going to throw the points randomly. How? You are going to generate random L and random, you are going to generate this and this randomly at a time. And then you are going to, for example, this point, each point has omega and has L. This is some L and omega, this is some L and omega, this is some L and omega, this is some L and omega. So let's say this point is omega 1 L1, omega 2 L2, omega 3, you get the idea. We're going to generate random points across L and omega That's just it. You're just going to generate random sum points, and then count how many of these points are inside, and you divide by the total number. And that's exactly how it works. It's really easy. In Python, you can do this in 2 lines. So how do you do in Python? First, so the algorithm now. So 1, define the square if you feel like you want it to be in the square. Define the square by randomly or not randomly, I would say, because first you will define the length and the width. Then number 2, randomly sample values from 0 to L and from 0 to W, because you're going to have, let's say this is 0, so this is W, this is L, right? For example, because area is length times width. So AS, area of the square, is length times width. That's the true area. But then you are going to randomly sample from 0 to L, from 0 to omega. Let's say here gives you, let's say L is 3 and omega is 4. Let's say here we sample L as 3 and omega as 4. So first random generation would be maybe 1, maybe L equals to 1 and omega equals to 2. So that's so L is 1, let's say this is 1 and this is 2, so the point should be here, that is inside. And let's say the second random sampling is like L equals 0 and omega equals 3, so that is L equals 0, omega equals 3, that's this point, and on and on and on. That's the second. So how do you do this? You do numpy dot random dot uniform from 0 to L n number of times. Oh, I forgot the n. So I should say here before number 2, I should say let's make this 3. So define the total number of sampling nt. So now you see we have nt, we already have as, which is, or I would say define the total number of sampling and the area, and the area as, which is L times W, 3 times 4, for example. And you're not going to the next, we can shrink this so we don't have to go to any other page. Let's shrink this down. Next we're going to number 4, going to determine which points fall, because we're already in this condition. We already defined the Yeah, so the L, the W, we already have. So now we already have defined the number of points we want to throw. So now we want to define these boundaries. So if this was a circle, for example, let's assume this is a circle. So cycle of radius r. So in this case, you will define NTA and r, so that you would say fall within r or less. So you are going to set conditions. So you can say generates random L N W, this one, and then you say if, so let's say this is equals to x. So if x is less than or equals to r, but usually you are going to set this condition, like, because it's a circle, you can say if L squared plus W squared, because equation of a circle is less than or equals to r, then this, you can call it, this is n in. So that's the ones that are in. That's all. You're done with the algorithm. And finally, I think I can shrink this so we can see everything at once. And finally, you can now say area of this object is n in, which is this, divided by n total, which is here you can set n total maybe to 1,000. You can throw double the points 1,000 times, and times the area of the square, and that's it. And you will find that this will approximate to pi r squared if you are dealing with a circle, for example, if circle was the shape you are interested in getting. The error of Monte Carlo method, the error is of order 1 over root n, or I would say 1 over root of n t. What do we see here? It is, sometimes you see the error as sigma divided by root n. This has to do with the sampling, because we're going to be sampling, and in most cases, if you sample a lot, it follows the central limit theorem. You end up with a Gaussian curve. But anyways, we'll talk about this later more. For now, this is the method. So in a nutshell, you can say the area of unknown object is the total number you are able to of points you are able to get in the object, divided by the total number you throw, times the object which you know. And that's it. And it's really easy. So if this is a square, for example, and you can put any object in this square and then keep throwing, and then apply this formula we have already demonstrated. How about in 2D? How about volume? This is area. How about volume? So volume of the object, we follow the same. It's the number you throw inside the object divided by the total number you throw times the volume of the known object. and for n dimensional you can say the same. N dimensional volume, so v n dimensional is n in over nt times the, let's say, some hyper volume known. This is basically the first part. Now we move to the second part. In this case I will divide here into. Now how can we estimate integrals using Monte Carlo method? So integration using Monte Carlo methods. It's easy. First, we know that area of object is number of those inside over total number you throw times the area of known. For example, let's say the known is a square, so you can say area of a square. You can transform this to estimate an integral. How do you do that? Let's say you are integrating from a to b some function f of x dx. And this is equivalent to finding the area under curve. This is, let's say this is x, this is f of x, and f of x is like this. You usually will have the values a and b here. So this region is the area you seek. You can do the same way we did. So what do you have to do? You find the maximum value of f of x and the minimum value of f of x, if it is here, if it is here, depending on where it is. And so what is the area of the known? So you're going to assume that this region is the object which you want to determine its area, and then this region is that square. And what is the area of this square? So area of the square would be f max minus f min. This is like the length L, and then the width is b minus a, and that's it. And you do the same thing. So now in the integral, so the integral I, so I, which now we will consider as a object, is n in. So then you are going to throw points, and then you set a condition. What is the condition? So the condition is, if the point is within this region, count it as inside. So this would be n in, and every other thing is n total. It's not supposed to be confusing this n total, because n total is considering all the points including n in. So n in is also an element of n total. Don't forget this, because the big square contains the shape, that's this shape, and every other space outside the shape. So n total is like, and therefore here you can say divide by n total times all of this times as, and that's the integral. Now let's make an example. Let's assume we want to integrate, let's say you want to integrate I equals integral from 0 to 1 into let's say square root of 1 minus x squared dx. Here our f of x is square root of 1 minus x squared, and minimum the minimum value is so f min, what is the minimum value f can get when x is 0, right? So f min will be 0 because x is 1 here, and then you get 0. What is the maximum value? The maximum value, because we are integrating between 0 and 1, the maximum value is when this is 1, when this is 0, and then f max is 1. This is just an example. Now, so when you're looking for AS, which is f max minus f min, you have 1 minus 0 for this, and b minus a. So a is, this is a, and this is b. So you're doing b minus a and minus 0 again. That's AS. And the next thing you do is you're going to generate random points on both omega and L. You remember? What is omega? Omega is from 0, because it seems like the maximum value here a is a is here. But anyways, you can always you can decide how you want it. In this case, we're lucky. We're very, very lucky. The fact that our function also in the mean and the max is corresponding to the limits. In fact, I would have given another example, but anyways, it's still fine. But I don't want you to get confused. Now, what we are looking at now here is, but first we have to decide how many points in total are we going to generate. So let's define NT as, let's say, 1000. And all we are left with is how to generate the W's and the L's randomly. So, and set the condition. It's exactly the same way we did here. Exactly that. So you generate randomly and then you set the condition, if you could remember. Now, regarding omega, you are going to generate random values from A to B. Regarding L, you are going to generate random values from F min to F max. NT random values here as well. NT random values. Random.uniform, for example. And then you set the condition. N in is that random value. You know it is going to generate, this is very crucial, you're going to generate L, and so for each L and W in this and this, sorry, L and W, or W and L, anyways, for each pair L and W, you are going to see is the value, because L is the one in the Y. So is the L less than f of x, which in this case is f of w? You get the idea? So you're trying to say, because some points will be generated here, 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 here. So we're looking at if there is any function, if the function exists, then you can find f of w, that is f of x, right? So if it is here, then you are going to accept this as a count, n in. Otherwise you cannot accept it as a count. So you are going to generate these random values L and W, and then you're going to, for each pair, see which one is less than, which one exists within the boundaries within which the integer f exists, and that's it. And that's it. So you literally have your I equals a object. Let me shrink a little so you can see. So I0, or I equals to a object, which is n in, which is this, divided by n total, which is this. You can, as many as. So the randomness comes in how you take the dimensions. This is a bit complicated compared to the easier one. I'll show you another easy way to do this. Times, in this case, times 1 times as, which is this. That is using the area method. But there is another method of integration, the simplest one. The integral from a to b f of x to x is it's just b minus a times mean of f of xi. This xi would be random samples from across a to b. That's all. So all you have to do is let's go back to our problem. Integration from 0 to 1. Let's say you have x squared dx. In this case, let's go back so you can see the formula properly. So the b is 1, the a is 0, the f of x is x squared, and then you're going to define your n. Yeah, of course, because you can write this as forgot to tell you, you can rewrite this as b minus a, because mean is like 1 over n nt times summation of f of xi. This is like mean. That's how you take the mean. So you have to define nt, maybe 1000, and that's it. And then you generate, so xi is numpy dot random dot uniform from a to b nt times, and that's it. And finally you can say that I, the integral, is just b minus a, so it's like 1 minus 0 times that. You can do np dot average of xi squared. That's all, and we shall see this in the code. It's easy, and you can use this method to integrate any function from a to b. F of x dx, this is just b minus a times the mean. That's the average, f of x I, where xi is random sample, or you can say randomly sampled in the interval a b. But you have to because nt is really crucial. That's the second method. In other words, you can look at this as b. This one you can look at it as b minus a f of x1, the first generated sample, plus f of x2, the second generated sample, let f of xn, the n generated sample, over nt. But anyways, you get the idea. Next we move to expectation values. So expectation. In fact, he's just trying to tell you how to estimate mean, averages. Expectation is also called average, or you can call it mean. This you can estimate. Usually, you can estimate like e of x. This is the symbol of how you represent expectation. So e of x naturally is integral of x times the probability of x dx, if you're dealing with statistics from a to b. And this is how it usually is. But I'll show you something. If you have a die and the outcomes of a die are 1, 2, 3, 4, 5, 6, that's the faces of a die. The die is something like this. I'm very bad in drawing, but you can see here can be 1, here can be 4, and all those. So this is like x1, x2, this is x6. So probability of x1 is 1 over 6, probability of x2 is 1 over 6, probability of x3 is 1 over 6, probability of x4 is 1 over 6, and on and on and on. Now the expectation of x, so if you're looking at e of 1, this is because we cannot integrate, so now we have to sum, and that's exactly what it does. That's exactly what it does. Yeah, but before we even do that one, let's take the average of this. What is the average of this outcome? It's like this, 1. So the average, you can call it maybe x bar. This is 1 plus 2 plus 3 plus 4 plus 5 plus 6 all over 6. And you can say, okay, 1 over 6 plus 2 over 6 plus 3 over 6 plus 4 over 6 plus 5 over 6 plus 6 over 6. And you can this is also expectation of x, for example. It's the mean. And you can say, but p of x1 is 1 over 6, p of x3 is 1 over 6. So that means you're doing 1 times p of 1 plus 2 times p of 2 plus 3 times p of 3 plus 4 times p of 4 plus 5 times p of 5 plus 6 times p of 6. And what do you notice? This is like summing. So the average is almost summing. You can say average is just the sum for I equals to 1 to 6 of xi times p of xi. This is what we are getting. And guess what? That is the expectation. So this is the summation form of expectation, and this is the integral form. And since it looks like this, Monte Carlo method is able to, you don't have to do all these things. Monte Carlo method says you can simply sample. You can simply sample. So you can simply sample and say the expectation of x, which is the integral of x p of x dx from a to b. I can simply approximate this using Monte Carlo method as the mean. 1 over n, I sum xi, where I is randomly sampled. I sample it randomly within a and b, nt times. Let's make this nt. You can also get the expectation of x squared. This is the mean, this is the variance. Expectation, this is not the variance, expectation of x squared, because the variance is it's from a to b, x squared p of x dx. This can be 1 over nt sum from 0 to n xi squared randomly sampled from a to b, and you get the idea. So how is the algorithm? It's simple. Just do numpy dot for the random sampling, but random dot uniform a, b, and t. That's all. That's x. And then you take the mean, np dot mean. This is too easy. It's xi, and that's it. You've implemented this formula instead of doing all of these things. And that's how interesting it can be. The same applies for this one. It is important to bear in mind that the error is of the order of 1 over n nt, and therefore when nt gets larger, the error shrinks. It's very important. So let's recap finally. So let's say summary. First, if you want to find area or volume, what do? Area of the object, or the volume of the object, is number of n over number total times area of the box, for example, or the square, or whatever. And you can also use this to estimate the integral. F of x dx from a to b. Then we also have another method of integration where you, from a to b, f of x dx, we approximate it as b minus a, mean of f of xi, where we randomly sample xi. In this case, the random sampling comes from here, because we're randomly sampling the length and the width. Here the random sampling comes from here. Here the random sampling, the same, comes from here. And this is going to be randomly sampled from a to b. This is the length, and then this is the width from 0 to L, and you sample from 0 to W, and that's it. N times, and then the expectation E, which is the average. We see that E of x is it's literally the mean, but you can put it to look more mathematical. F of xi, and the random sampling. You randomly sample because this should be from A to B, x, p of x, dx. So you randomly sample. And the same applies to, and then we know that the error is either sigma over root n t, or you can just say is of the order of 1 over root n. It's just trying to tell you that the higher it goes, the lower you get. There is also this confidence interval that I did not touch. So the confidence interval is estimate, whatever you estimate, plus or minus 2 sigma over root n. Yeah, that's the confidence interval of Monte Carlo simulation.